Hello, everyone. Welcome to our second SERC talk of 2020 and the second talk of our three-part autonomy and trust series. Tom McDermott is our Deputy Director and Chief Technology Officer of the Systems Engineering Research Center at Siemens Institute, also known as SERC. He's a lecturer on systems thinking and leadership development in Georgia Tech's Professional Education College and consults with multiple organizations on enterprise modeling for transformational change through his research and consulting practice. He's also recently the elected Director of Strategic Integration for NCOSI and has over 35 years of background and experience in technical and management disciplines, including 15 years at Georgia Tech and 18 years with Lockheed Martin. He also currently serves as the Principal Researcher and Interim Director of Research at Georgia Tech Institute. From 2002 to 2018, leading unprecedented growth and repeatedly being named one of Atlanta's best place to work. And there's more information that you can find on our website about Tom. And Dr. Peter Beling is the Professor of Systems Engineer at the University of Virginia. In addition to serving as a SERC Research Council member, providing guidance in trusted systems research area, Dr. Beling's research interests are in the area of decision-making in complex systems with emphasis on adaptive decision support systems and on model-based approaches of systems design and assessment. His research has found application in a variety of domains, including mission-focused cybersecurity, reconnaissance and intelligence and surveillance, prognostic and diagnostic systems, and financial decision-making. He also directs the University of Virginia site for the Center of Visual and Decision Informatics, a National Science Foundation Industry University Cooperative Research Center, and the Adaptive Decision Systems Laboratory, which focuses on data analytics and decision support in cyber-physical systems. Again, I appreciate you bearing with me. With that, I'll let Tom take over.
Thank you. We're going to shut off our video while we talk, just to conserve bandwidth here. So today the question was, can we assure resilience of cyber-physical systems using model-based system engineering? And Peter and I, we're going to tag team on a briefing that talks about a body of work that's been going on in the SERC for some years now, and is starting to transition across the community. So we're interested here in resilience of cyber-physical systems. And this is a bit different problem than what IT security deals with. Typically in the cybersecurity domain up till now, dealing with IT systems, primarily the approaches have been protect the infrastructure, but not worry about too much about the applications that are going on inside, and protect the information from getting corrupted or getting out of the system. Cyber-physical systems are a little bit different. They have control processes in them. They have control processes that can do damage or harm people. And the infrastructure, although protection is important, the cyber-physical processes, these control processes, are applications, and they have to be protected directly. And so we want to use system engineering to look at how to manage and protect those control processes. The cybersecurity community to date in the IT domain doesn't really look so much at system application functions or control functions, and so they have limited experience in this space. While as the engineering people that do control system design don't necessarily have much experience with cybersecurity itself. And so we have this gap, and we've been trying to fill this gap for a number of years now, specifically focused on resilience of cyber-physical systems. This is kind of a history chart. So some of the things that have transitioned in the past, I'd say this research started back in 2013 with this idea of system-aware security architecture patterns. And so the idea here was, could we devise patterns that could be applied in a system architecture that would first monitor for the cyber threats and then apply different types of behavioral control to the system take action in response to threats, and we call those sentinel patterns. And that started off as mostly a manual process, but it was effective. So we did prototype demonstrations in a number of different domains. You can see some of them here, to where we were able to prove that the systems in a red team setting were protected. And out of that process came a standard cybersecurity requirements methodology, which again was pretty manual in the beginning, but now the research has started to focus in on how to capture that process and its resulting patterns in a model-based system engineering environment. And we'll show you that both in terms of a description and a demo later on in the briefing. The SERC has a roadmap for what we call trusted systems, so trust in cyber-physical systems. And I'm not going to go through the details on this, just the research is following a roadmap. I'll just mention some things. So one thread of this roadmap is looking at how do we standardize on assurance methods across security, but also safety, reliability, and other things. And we're looking at that as a combined set of activities. The second thread is, can we actually make those decisions up in the early stages of the system design at the architectural level or early in the requirements phase? And so what tools, modeling tools, would we use for that? The third thread is then looking at, can we formally validate the assurance decisions in design, build, and test? And we won't spend all our time talking about that today. And then the fourth thread is, can we integrate cybersecurity into the engineering roles and skills and engineering education where it's pretty lacking right now? And we won't spend much time talking about that today. Just going back up a little bit, this is a picture of some work that was done by Barry Bain on system qualities and ontology in another research project. And when we talk about resilient systems, you can see kind of the complexity of system attributes that we're dealing with. So to get to resilience, we have to work a design phase that assures that those systems are dependable and they're available in the presence of threats or other different types of failures, which links into the concept of them being reliable and robust and other things. And so if you work your way down this chain, you can see that implementation of security and safety and other such abilities in the system, these are design choices. And we use the term maximum reasonable assurance to describe the output of that design. So we can't predict everything and we can't assure for everything, but we want to make sure that we've done the maximum reasonable amount of assurance given cost, schedule, all these other things that drive programs. And so what we really want to do is we want to capture this process of working our way up through these abilities in the model setting, and we'll show you that. Once you have that, then you have to consider the importance of system validation as part of that. And so the testability and modifiability and changeability of the systems is another area of research that we won't get into as much today. This is one view of how threats and failures get into systems. The key part of this is mission level resilience. And so we started calling this system aware, we call it mission aware security now, because we're really interested in resilience, meaning can we meet our mission objectives and continue on the mission or abort it as needed. And that's the driving requirement set. And if you do a normal top-down decomposition using a mission function and task type analysis, mission objectives then decompose into operational tasks, which then we can decompose into system functions. And then those are decomposed down at the design level into system assets, hardware and software, as well as the information assets that those use. And so what we want to do is ensure that we have a good system engineering model of that decomposition captured in the phase. If you think of this as a bottom-up process, then system assets are the things that get impacted. And if it's a reliability issue, for instance, it may be a physical failure in the system. If it's a software, it may be an information failure in the system. So they come up from the bottom and they propagate through the system back up through functions into tasks and missions. Cyber threat enters through a physical system asset, but it propagates up through the system the same way, through compromise of information and then compromise of functions or tasks as it goes up the chain. And so, although you can see that the threat behaviors are very different at the bottom level, the way they propagate through the system in terms of a system model might be very similar. And so the core concept here is that we ought to be able to apply patterns in the architectural design that are in response to either type of disruption to the system, but they're common in terms of how they're implemented. And so a lot of this work is trying to find those patterns. This is just a kind of a generic view of how threats propagate through systems. And so threats enter by taking action, and they take that action based on knowledge that they develop about the system. And so the knowledge that they develop allows them to select different pathways through the system. These would be known as contextual selection factors. And those lead to other actions, and as they propagate through the system, there's these branch points, and so it gets very complex. These end up coming out at the other end as sets of responses that the system can take or the human can take, which are other nodes in the graph, and these are functions themselves as you go through the process out to the end where the final action is taken. And we show this graph representation of it just to understand that this is a very complex process. And one of the reasons why we want to go into model land is we need to be able to simulate this and eventually automate it because of its complexity. And so the idea here is that well-defined system structural and functional models, as well as well-defined threat functional models, allow us to create these graphs and in fact extract the graphs out of a SysML model, if you want to think of it that way. So you look at these as kind of two different views of the system. The mission aware process was developed several years ago, well, actually dates back to 2013, with this kind of idea that given that we have a system and we need to detect and protect it from threats, we can bring it into a mission requirements process where the system itself is modeled, and then the control functions and associated loss functions, if control goes haywire, are modeled, and then red team and blue teams can, in a tabletops, go off and iterate on these models. So we take that, primarily human process into a systems modeling environment, and the idea here is to capture the whole of that into a common systems model in various forms, and so you can simulate that. At the same time, we want to actually create attack models. So we want to model the attack structure for the cybersecurity aspects of the system to get in and link those into the system model to create a set of decision metrics at the end and loop back through this process. And so this is the basic role of the mission aware process, which we've implemented. So at this point in time, I'll turn it over to Peter Beling, and he'll walk you through the actual cyber requirements process.
Yeah, thank you, Tom. So welcome, everyone. The process of designing for cyber resilience is something that, as Tom mentioned, we began thinking about in around 2013. And we were doing that in the context of a military UAV, kind of large drone. And when we sat down to think through a system like that with all of its components, its supply chain, its software, its points of physical entry and potential insider threats, we quickly came to the conclusion that we couldn't protect everything. And so that raised the question, then, what do we want to protect? So what choices are we going to make, and how both among the system functions that we'd like to protect, and in terms of the ways in which we'd go about offering that, providing that resilience through system design or potentially the addition of components to the system. So when we considered that question, that led us to the idea that, well, we're going to need a lot of help to answer something as complex as that. When you take a complex aircraft like one of these drones, and then you embed it in something even more complex like a mission. And so what we thought about was bringing together 3 different teams of stakeholders and or experts. So in each of the cases, what we imagined was providing the team with something in the way of tools or output from one of the other teams, and asking in return for something that was useful for the overall design process. So the blue team consists of the system and mission owners. So it might be people who know a lot about how the aircraft was made, but it might also be the people who own the mission, right? And who are using it in the field. And so what we provided to the blue team is a structured elicitation process, and we'll describe what that is in a little bit later. It comes from the safety community, and what that allows the blue team to do is to come up with a set of priorities, the kinds of things that keep them awake at night in terms of loss of system function. So these are the things that they want to make sure that that it is not lost in terms of system functionality. And so I'll give an example, and Tom is going to walk through a kind of detailed example of what might come out of a blue team, and indeed all the other teams a little bit later. So the scoping of understanding what's really important is essential for the systems engineers, and the systems engineers have 2 principal jobs: to take those requirements and turn them into a resilient design, to use them as a basis for constructing an initial resilient design, and then documenting that design, doing this all in the context of model-based systems engineering. And once we have a design, then the question becomes, how good is it? What kind of vulnerabilities might still exist? So to assess that, we end up using a red team, and the red team is structured in such a way that we're really pursuing the hypothesis that the red teamers are going to do a better job the more that they know about the system. So we provide them with the output from the systems engineers in terms of model-based systems engineering description of the system, in terms of descriptions of the requirements, so they can understand, as they're poking around for vulnerabilities, what really matters and what doesn't matter. So that next slide, please, Tom. So that kind of loose process is something that we first standardized in something called the Cyber Security Requirements Methodology, CSRM. You can see the colors in this flowchart really represent the 3 different teams: systems engineering, red team, and blue team. And again, the idea is that the blue team gives us an operational risk assessment. So going back to our UAV example, one of the things that we did initially is ask owners of UAVs, hey, what is it that keeps you up at night? What do you really care about? And the answer we got back is that, well, we're not too worried about the aircraft being shot down after, or crashing, because people are shooting at it kinetically anyway. So as a cyber threat, that's not the largest thing out there. We're not worried about losing mission, not receiving our mission data because we have other sources of getting the data. But what we really care about is making sure that that drone ends up going the places that we tell it to go, and that it doesn't, for example, go off and fly into enemy territory. That's a principal kind of a thing that we couldn't tolerate. So having that kind of information from the blue team then allows the systems engineers to go in and make an initial resilient design, saying, okay, how are we going to keep the UAV from flying into enemy territory? That maybe means protecting the navigation system, and the navigation system relies heavily on GPS. What can we do about that? One idea is that we could harden the GPS units in a conventional cybersecurity approach to that, but that's a very complex thing. If we instead note that typically the UAVs that at least we were looking at have 2 GPS units. So a very simple resilience concept would be, and a design pattern here would be to take the 2 GPS units and compare their outputs using a simple voting mechanism. And if they agree, then we continue the mission as normal. And if they disagree, then we do something different. And what that something is also something that's going to have to reflect the priorities and interests of the blue team. So the systems engineers are in charge of that, producing an initial design, which is then evaluated by the red team. And the red team, again, has access to the full system model, and also potentially to access to other things, as I'll mention in a few minutes. And the notion is then we iterate that process. So that's our manual process, and we'll get to something a little bit more formal in a bit. So next slide, if you would, Tom. So the key concept that we're working with in terms of resilience is illustrated in this figure here, where what we're relying on is a broad kind of idea. It's not the only idea in the world, but it's a fairly general kind of notion that what we're doing is watching the system and how things are unfold in terms of the functions that it's performing and and the behavior that it's exhibiting, using something that we call a sentinel. And a sentinel, an example of sentinel would be something that's watching and comparing the outputs of the 2 GPS units on the UAV. And when there's a difference detected, then the sentinel engages in a reconfiguration control and puts the system into a different mode of operation, a resilient mode, which could range from, okay, we're switching from GPS-based navigation to inertial navigation, to we're forcing ourselves to land, to we're going to self-destruct. And it could be anything on a very broad spectrum. And again, these resilience modes are things that come out of the system owners and mission owners' priorities and interests. So this is our broad mechanism for providing resilience. And I just want to mention one other thing about it is that when you have a concept like this, the Sentinel watching simple things like the outputs of GPS units, then you can make a simple Sentinel. And a simple Sentinel can be made very hard. So it itself is not really a major attack vector for the system. So that the Sentinel might involve only a couple hundred lines of code, and it might run on something like an FPGA instead of a general CPU. Okay, next slide, Tom. So there are lots of potential resilience modes and detection patterns that we've considered, and others, Siemens and Stevens Institute of Technology. And I don't propose to go through all of them, but there's a list here available on the slides, and there are many others that we as a group have considered in this kind of context. And we're starting to build up a pretty good library of the different mechanisms for, again, both monitoring the system and for those resilient modes of operation. So next slide, if you would, Tom. So I mentioned the red team and our desire to provide the red team with information on the system. Actually, what we really want to do is provide the red team with two kinds of views of the world. One is the systems view, and we express that structurally and to the extent that we can functionally as well, and do that with SysML-based models and things that are exported or derived from that basic kind of structure. So for example, GraphML and other kinds of graph views of the system. And the other thing we want the red team to have access to is an understanding of what the threat space might be, at least as reflected in something like the historical databases. So for example, MITRE's, CAPEX, CWCV databases might give the red team some insight in how to think about what kind of attacks and what kind of attack vectors might be out there and how those cross-reference with the system that we have and the system as described in terms of our priorities, right? The outputs of the process where we kind of narrowly focused around the things that really matter, like not flying into enemy territory. So this work is something that we call the cyber body of knowledge, and it was done by Virginia Commonwealth University and Dr. Carl Elks. So next slide, please, Tom. So I'd like to now describe how we're moving towards a more formal kind of process in the model-based systems engineering world. So our mission aware kind of idea, it folds together three different components. So model-based systems engineering, and in particular, we're aiming for something that doesn't quite exist yet, SysML 2.0, but we have products that are in a framework that's headed in that direction. STPA, which is an elicitation process and hazard kind of analysis that comes out of the safety community and has modifications for security. And our own perspective that I've just described of having the Sentinel and the kinds of analyses and teams that we just went over. So all of that comes together in our model-based systems engineering meta model for Mission Aware. So next slide, please, Tom. So yeah, let's just go through some of the inputs. So first, STPA, this is something that comes out of Nancy Levison's lab and has a long history in the safety community. And the idea is that maybe what we want to do is look at things like accidents and losses. The loss of something that's of value to the stakeholders is not an event, but the outcome of a process. So what the idea is that we could take a group of stakeholders for a system and walk them through a process where they're thinking about what it is that keeps them up at night. What are the losses that they're really concerned with, and not everything, but the top ones. And then begin to understand the hazards that are associated with those losses. So those are the system states at the time or just before the losses are realized. And then the notion that, again, because we're thinking about things as a control process, what were the control actions, we call them unsafe control actions that led to the hazards. And then finally, what is the overall kind of loss scenario? And if we can begin to understand all of these elements, then we can begin to shape our model-based systems engineering in the direction of that hopefully allows the most useful expression of requirements and concerns on the part of the system stakeholders. I should mention that with STPA comes other modifications that have come out of this community, including STPA SEC by Colonel Young and STAMP and other things. So we're enthusiastic adopters of all of this kind of work. So next slide, please, Tom. And so the second component that we're folding into our overall model is a meta model for kind of all systems, which is an ambitious thing. Unfortunately, we didn't have to create this, but we've adopted it from a company called Vitec. And Vitec has the meta model that's shown here that is sort of a result of them thinking about systems over a very long period of time. And what drew us to this meta model is not only the coherence and utility of it, but also the fact that it's aligned with what we think SysML 2.0 will end up being. So it reflects a lot of the ambitions that people have for SysML 2.0, which is still evolving as a standard. So we feel like this was a good starting point for us, representing what the open source community will be in the future, and we could substitute as those open source models become available. We can substitute them in place of Vitek's model, but for the moment, we're really very happy with this this view that Vitek expresses. And the notion here is that this meta model expresses all the aspects of systems, from requirements through functional elements, physical elements, and I can't go through all of the aspects of it in the interest of time, but I'll just say that it has a great deal of utility associated with it, including notions of layering and hierarchy that allow for one to go beyond just an architectural view to really seeing processes and how systems work. So next slide, please. So our extended version of that model includes all of the elements of CSRM that I mentioned earlier. And you can kind of get the feel for that by looking at this diagram and seeing the elements that are in tan. And all of those tan elements are the things that we talked about. So for example, over on the right, there's the STPA process is easily identifiable, the losses, the hazards, the unsafe actions over in that range. The Sentinel is over to the left, and the Sentinel is working to put the system in and out of resilient modes. So all of those kinds of elements have been built into our meta model here, and the ontologies we've defined for what the meanings are associated with these links. And rather than trying to walk through this in the abstract, what Tom and I think would be best is if we turn to a specific example. So I'm going to turn it back over to Tom at this point, and he's going to walk us through an example that will bring this to life in a detailed kind of way. So Tom, it's all yours.
Thank you, Peter. So we're going to walk through an actual model that's organized like this. So we've organized the model elements into packages that describe the system model as architectural or structural and behavioral models, the assurance model, which we call risk, the system aware model, mission aware model, which we call resilience, and then the threat model. Before we do that, just a couple concepts. So one way to think about this in a model sense is that you have your system model, and then you have your mission aware model, and then you have your cyber threat model, and those things are simultaneously modeled and linked. And so an attack from a cyber attacker on the system then is monitored and controlled by the mission aware system. And so in just a general view, that process is a functional process. And so here's a simple generic process where a system is started up. It runs two tasks. You can think of this as a couple of servers, and those tasks consume CPU time, and then there's CPU idle time before the processes are stopped. And then you could envision a cyber attacker that has placed malicious software dormant in the system until it becomes active. And then what they're going to do is execute a denial of service attack, which is going to consume the CPU time. And so the mission aware function can then monitor the CPU idle time to determine if there's a cyber attack, in which case you go into a resilient mode, or if it's operating normally in that space. So an example of an action it might take in those cases would be to stop the existing server and start a diverse redundant server to come into play. So we'll walk through something like this. I'll just mention it is simulatable, at least in terms of process steps through that process. The last project we've been working on is really started to look at complex system of systems, and we've been really interested in how we can do trade space analysis. So we want to understand things like the cost benefit to the threat with relationship to the decisions that have to be made in the system, particularly to add these resilience features, which also have cost and benefit associated with them. And so this is the scenario that we had going into this project. You can imagine just reading through this, but the outcome is that there's 3 major pipelines that take oil from the wellheads to the refineries in the Middle East. And if you were able to insert malicious attack into the system as an advanced persistent threat, and then take advantage of a set of events, then you could degrade the flow. We estimated, or the students estimated, that you could impact global oil availability by 10% if you could decrease the flow through these 3 pipelines. And if you could do that for 30 days, you would increase the price of oil by 50%. It would have a $31 billion market price impact, and you could make a lot of money in oil futures. And so here we kind of take a scenario where we can sort of explicitly get it down to things like cost metrics. As we went into this process, this concept of a ConOps becomes important, whereas we were doing mostly tabletops before. We're envisioning a threat where an advanced persistent piece of malware is placed in a SCADA system, controlling the flow to the pipeline, and is combined with a human attack in real time that actually impacts the maintenance on the system. And so you can envision keeping it inoperable for a long enough period of time in the distribution control, where you dissipate stored oil and you have an impact on oil and gas. And what we found as we went through this process is that a formal ConOps document ends up being the best way to capture this description to get down to the engineering level. And so you can think of this as the blue team developing this ConOps document just by table of contents. It's like a regular ConOps document. You describe the system as is, but instead of describing the new capabilities that you want to put in the system, you describe the capabilities that you want to put in the system to counter the threats or the safety concerns. And so, so we built this ConOps document. It seems to be a good formal process going in that space. And I'm going to switch over to the model now, and just walk you through some things. So this is actually going into an executable of the model. The Genesis tool allows you to build an executable for review purposes, and this is running in GitLab. And so we've organized all these different components of the model that are part of our meta model into sets of packages. And so you can see this is the yellow team. The yellow team has the system architecture and behavioral modeling, and then you have the blue team that's looking at the risk, and you have the red team that's looking at the cyber impacts, and then they're determining these resilience features. And so it can be built as a nice set of data linked in together in sets of models. And so you can start with your normal system engineering process, and we can look at the system context, and you can kind of see here within our model, we're modeling the mission aware system and the oil and gas pipeline system in the presence of its physical environment, its connectivity through a wide area network, its connection to a security operations center, the endpoints, the wellheads and the refineries facilities, and then an advanced persistent threat in the space. And so we can look at it in terms of those kind of things. And you can see it in terms of the external views, and then you can see other views that if you want to go through that are part of that process. So this is what the system looks like at the pipeline level, but we're really interested in driving down to what would be known as our route segment. So a route segment would be a piece of pipe, and that piece of pipe would consist of pumps and valves and sensors that are all managed through a SCADA system connected to a LAN, and then managed through a human segment controller. And we also actually have to model the maintenance system. So this thing called a pig is a thing that's inserted into pipelines to clean them out. So we've captured at a high level in this model all those major components. The key thing then is to get it into the functional view. And so, so we're interested in route management, which is where the distribution attack would happen. And so now you can see we can bring up the functional flows associated with route management. And so this is an item, route request, that goes to a route manager at the segment level. And if we drill down into this a bit deeper, then you can see the properties of that stuff as we go through. The operator functions themselves then can give us the details similar to that other attack model of how one might work their way through this system. And so you can think about giving this particular model to a red team as being an asset to where they can start determining how, once they have entry in the system, that they might flow their operations through the system itself. So that's the system engineering part. You can see how he modeled risk, and so we're interested in here in can we change flow rates? Can we change direction and other things in flow rates? And so we can actually look at the components of the loss model. And so if we misdirect flow rate in a pipeline segment, then we cause an unsafe action, which can lead to a set of hazards, release of content, equipment operated outside of its boundaries, and shut down. And you can see that's associated with the context, the overall pipeline system state, and this control action, which we've modeled through the STPA process. And all these things can lead to different kind of losses. This is important. It's so people injured or killed have happened in pipeline accidents, not to our knowledge because people actually intruded on them, but because software errors caused these unsafe actions to happen in the past. So that's how you capture the hazard. And then we can start looking at resilience modes. But first, let's kind of look at the cyber threat. So, so there's two threats that we're interested in. And one is a command intercept, a man-in-the-middle attack on the route manager, and the other one is this inspection fraud. And there's not anything modeled specifically here, but if you look at the data sheet, you can see the aspects of the meta model. So we're going to monitor this by monitoring SCADA messages from different SCADA controllers. We've linked the threat itself to a KPEC behavioral model, which is a malicious logic insertion into the SCADA system. Here's the Sentinel protection strategy. Here's the resilient mode and the unsafe action. And so all these things are linked together within the modeling environment. And you can see the components of that threat as you go through the process here. So you can see the links, and then you can see the particular attack vector as part of it in the space. So if we jump back up to the resilience mode, then we can look at how we can employ different types of resilience modes into these route strategies. So you can have a diverse redundant manager that employs multiple SCADAs to check on the system. And you can drill down into these things, sorry. Click the wrong button. But you can drill down into these things into different ways and see how they're all connected together. And we haven't modeled this all the way down in the space. So as a result of this process, then we get kind of a full system model that links all these components together. So I'm going to jump back into slideshow mode here. I'm sorry. And so now that we've got the whole system modeled, then we can start looking at resilience evaluation metrics. So we can start setting performance requirements in the system that are determined by different teams. So the loss scenario, for instance, the red team determines how the likelihood of the attack, but the system model determines how much time it's going to take for the resilience mode to detect that attack and respond to it and then isolate it. And so we can start modeling these metrics as we go along. And as we conclude through this project, we're trying to link these cost metrics into more of a trade-based point of view. So, and the last slide here. So our goal here is to get a consistent methodology built on standard system engineering tools. And we're actually publicizing this out now because we would like programs to work with so we can start transitioning and using these tools. We have one transition partner in the Army now, and we'd like to get some additional transition partners. And once we have more transition, then we can start looking at how we can implement the models to do more standardization of process, to build automated tools to look at scalability, to link directly in a model sense into operational test and evaluation activities, and then to build good trace-based visualization tools that help us see cost and risk in the space. So I'll stop there and we'll turn it over to questions.